Hi, everyone. My name is John Morgan Manos. You might hear JM. A lot of people call me by my initials, JM. I'm a PhD candidate at the University of Washington, and I'm not actually a JERPer. I've never been to JERP or the Juneau ice field, but I am excited to work collaboratively, potentially with you guys in the future, and interested in JERP as a proving ground for new technologies. And a lot of my research is based on distributed optical fiber sensing or distributed acoustic sensing, or DAS is a type of distributed optical fiber sensing. And just to motivate why we're interested in taking in situ measurements of glaciers as well. One, glaciers are losing mass virtually everywhere, and in Alaska, particularly, is the main contributor right now to sea level rise. And you know, by 2100 is projected to lose most, if not all, of its glacial mass. Yet models and satellite observations still require in situ validations and observations, and they also help reveal the mechanisms of ice flow or mass changes that otherwise remote sensing technologies might miss or not be able to capture entirely. Trying to switch slides. Okay, here we go. I think Kaya set up this part of the talk pretty well. The traditional limitations of in situ observations typically revolve around instrument integrity in the field. So seismometers and old seismometers like these can easily tip over. They can melt out in high ablation areas, and you might not realize that is happening during the course of your measurements. And also the spatial resolution can often be limiting. Accessing and deploying locations in a distributed sense can be time consuming. They might not always be accessible. And the aperture, or how far they can sense, or how wide an array you can sense, is also can be time limiting to deploy. And so that kind of necessitates trying to think of a different way or a new technology to go about sensing these important mechanisms. And so for that, we turn to fiber optic cables. Uh, Fiber optic cables are virtually ubiquitous in today's environments. This is a map of the undersea telecommunication fiber optic cables, and so the Earth is covered in a web of fiber optic cables. And so one aspect of this is that the cables themselves are very robust. Um, but we can also, in some ways, leverage the already deployed telecom fiber network to do geophysical sensing. And so this has been done looking at ocean waves and the sediment structure in the ocean using what's called dark fiber or unlit telecom fibers. Volcanic and slope stability hazards have been studied. One particular project around Mount Rainier has used telecom fibers that have run up towards the mountain, and avalanches. So in Switzerland, they've looked at avalanches and debris movements, snow movements from telecom fibers that go over the mountain passes. So we can utilize the already deployed networks for geophysical measurements, but we can also, and much of my research has been deploying my own fibers. So we can procure and deploy fiber optic cables ourselves. The cables are relatively cheap. You can get kilometers of cable for just a few $100s, or like maybe a couple thousand if you have a really armored cable. And so here is a picture from two pictures from Ronan Glacier on the left, a fiber optic cable that's deployed in the snow. Part of the cable runs over the ice. And then you can even deploy the fibers vertically in boreholes. So this is a picture on the right of me deploying a fiber optic cable on combatant coal. It's an ice rise alpine glacier in Canada. And so the fiber cable itself is actually strong enough, rigid enough to be lowered and weighted in a borehole. So you can get virtually all aspects of geophysical sensing, directionality at least, using fiber optic cables. Now, DAS, the actual technology, what it does is pulse a light, a laser down a fiber optic cable. On the bottom schematic, you're looking at the internal structure of a fiber cable, and the light is really scattered off of density perturbations or impurities in the glass itself, and then some of that light is sent backwards toward the interrogator, and we can measure the phase of that backscattered light. Um, and the rest of the file, the rest of the unscattered light continues down to sample more of the cable. Now we can do this repeatedly, so we can send thousands of pulses down the cable a second and measure the phase shift through time of the return light continuously along the fiber optic cable. And then that then translates to a strain or a strain rate measurement. And so effectively what we have is a one-dimensional seismometer, kind of continuously thousands of them along this fiber optic cable. We can sample down to a meter or 10 meters in that range usually, and then temporal sampling. We're sensitive to signals down to the millihertz range-ish at a threshold, and then we can sample up to 60 kilohertz on the interrogators that we use. So at the Nyquist, sensing signals to the 30 kilohertz. Now, on the aperture side of things, we basically the limitation is the power of the interrogator and the light traveling down the fiber optic cable. And so we're virtually sensitive to the decay of the light in the fiber, and so can go up to about 100 kilometers. So basically, since you can deploy these cables along the flow lines of most glaciers and capture the entire flow line. And so that's what we did in Ronin Glacier. So this was part of one of my projects during my PhD, was to measure the ambient noise of the surface of the glacier. So on the right-hand side, you see the map of Ronin Glacier. The fiber optic cable was deployed along the flow line. And on the left, if you're not used to seeing DAS measurements, this is called a waterfall plot. So time at the earliest time is at the top, and then the oldest time is at the bottom. And you can see the x-axis is distance or also channel number. So distance 0, channel 0 is at the interrogator, and then going up to the accumulation zone is at the far right. And so what we see are these nice diurnal pulses of acoustic noise. So the brighter colors are higher strains averaged over time, and those correlate well with the discharge. There's also pulse amplitude changes in space and time. So the surface of glaciers are inherently non-stationary. So the noise sources are going to change through time. And so one of the benefits of a fiber optic cable is that it can be deployed over the entire flow line and thus sensitive to those changes. And wherever the surface water moves, wherever the noise moves, the cable will be also sensitive to that wherever it goes. So we don't really lose sensitivity necessarily based on the changing spatial acoustic wave field. Now, because it collects so much data, it's kind of hard to analyze it, interpret it manually. So we pass this into a machine learning algorithm that we built. And at the top plot, you see what's LSTM being the machine learning model that we used. Passing in the DAS data to use the machine learning model to predict on the discharge that we had recording at a proglacial stream. And we can see that models trained on DAS performed quite well. And then comparing it to models trained on just weather data that we had measured in the vicinity, and then also a positive degree day model that the DAS models perform much better than those. So it's useful in terms of, supplementing potentially other styles of glacier discharge or glacier environmental sensing methods. So we can also sense the short-term changes to glaciers. So we're not only looking over the entire melt season, we can also sense the elastic properties of glaciers or detect ice quakes. So this is an experiment that happened at Eastwind Glacier in Antarctica. It's about 40 kilometers outside of McMurdo Station, and a fiber optic cable was deployed across the grounding line there. So here we were interested in sensing the dynamics and changes at the grounding line over this short observation period. The cable was sensed a year after it was deployed. There was one measurement done prior, just after deploying the cable, and then we instrumented the cable again a year later, and the cable was still in good integrity and was able to be used for a second measurement. So it was well coupled to the surface at that point. In this area, there had been about a meter of snow. You can see the flag barely sticking up out of the surface, but thankfully the end of the cable is still retrievable and able to be measured. Here is an example of an ice quake. Again, a waterfall plot being here the distance closest to the interrogators on the bottom going up in optical distance to the top. And then you can see the wave field changing kind of orientations as that cable is changing orientations on the surface as well. So again, it's a one-dimensional seismometer effectively, but it's only sensitive to the longitudinal direction of the fiber. So you have to be kind of cognizant of that when you kind of look at these plots. Uh, we sensed over 80 events just the course over 12 hours of recording, and the data itself is fairly high quality. You can see clear separations of wave phases, so a higher frequency wave, faster wave arriving first, and then slower slower waves, lower frequencies arriving a bit later. And so the wave dispersion and reflections can also be useful for determining seismic velocities and also the characteristics at the grounding line. You can use this type of data to constrain source mechanisms. So following on from this work, we hope to create moment tensors, which would be fairly unique with DAS data, and DAS could be a good supplement for the conventional nodal arrays that um, are deployed in glacier environments. Just locating all of those events as well. We can do that with the DAS and the directionality of the cable. We did this using a Markov chain Monte Carlo algorithm, and we see that they're located relatively well and then can be attributed to different parts of the glacier or potentially different mechanisms that are causing these ice quakes. Some like things like grounding line seismicity. You can see a lot of the events plot right at the grounding line. Shear margin crevassing. There's crevasse fields kind of on the grid east and grid west of the glacier here, flowing into the McMurdo Sound. And then potentially crevassing that's either happening on the ice shelf itself, either basal crevassing, basal rifting, or potentially flexural gravity waves of the ice shelf. Looking at the frequency of these events through time, we can start to correlate them to tidal modulations. So the rising arm of the tides, you see there's less frequent events when compared to the falling tides, and that kind of is a known property or a mechanism of increasing friction as the tide lowers the ice shelf and increases the friction of the glacier on the grounding line or on the bedrock it's sitting on. And we can kind of use this, and this has implications for all glaciers that are essentially flowing out onto ice shelves and inherently their stability too over time. One cool thing is that we can do DAS and what's called distributed temperature sensing, DTS. They can be co-located, deployed together. So many of these fiber optic cables, you can have multiple fibers running in the same cable itself, running in the same jacket. So you can do temperature sensing, strain sensing at the same time, and then do comparisons between the two as well, which is can have some powerful observations. This is a cable that was deployed in a fjord in Greenland and had been published on by a postdoc in our lab, Dominic Graff. And so you can see at the top plot is temperature. Again, distance and optical distance is going from nearest to the top to farthest away, deeper in the fjord at the bottom. And you can see on this vertical section of cable that there is in the temperature plot stratigraphy in the temperature or internal waves, and that those layers in the fjord are there's waves that's actually bobbing up and down. You can see that the temperature is going up and down through time, and if you zoom in on the right-hand plot, you can see that those waves in the temperature are also co-located or correlated with the DAS strain. So you can see compression and extension and strain of the cable mirroring the internal waves of the fjord. So I think this has quite a lot of interesting applications. So thinking about deploying a cable on the surface of the Juneau ice field, you can get seismicity, strain on the surface glaciers, sensitive to melt. You can listen to the melt being produced and percolating through the snowpack, and then also potentially deploy a DTS as well and get see how that relates to the surface temperature of the snowpack. DAS in general is a light and fairly cost-effective solution once you buy the interrogators. The interrogators themselves can get fairly expensive, not so much, I think, anymore, like something in the 50,000 range nowadays, but they're getting cheaper and they're actually quite light. So the interrogator plus a 2 kilometer fiber optic cable can be less than 100 pounds. So this is an example of it being flown up to combat cold, the glacier via helicopter, getting all of the equipment that we needed on one load, in addition to other equipment. So it's not prohibitively it doesn't need a whole lot of equipment to function well. And the newest generations are even getting smaller and require less power. So typically, interrogators require somewhere in the 100 watts of power. Bigger interrogators that have larger internal storage might require a little bit more, but there are lower power solutions that are being developed that are specifically for geophysical sensing. And so I think a lot of the manufacturers of these equipments are kind of catching on to the viability of geophysical sensing with these interrogators and are now kind of gearing some of their developments for geophysical measurements and things that we require as geoscientists and data management, other requirements for those. They're also developing them with auto power on and off settings, so you can effectively set this to turn on and record over a short duration and then power off to a low power setting. So thinking about how this might be deployed in the future, field setting over longer time periods, you can have trigger-based saving of data, so then you don't have continuous files running up into the tens of terabytes saving onto the interrogator itself. You can basically limit your saving to only the events that you're interested in. And then the DTSs also have this power on, power off that you can effectively take measurements, say once in the peak heating in the middle of the day, and then one in the min temperatures at night. So you can limit your sampling basically to whatever you need and whatever your requirements dictate for the project. So just to summarize real quick, DAS turns fiber optic cables into a continuous array of thousands of one-dimensional seismometers and can be quite powerful in many different geophysical settings and glaciological settings, kind of sensing glaciers and their motion and their mass changes through melt and snow and accumulation time periods during the year. It offers flexibility in sensing, over short duration deployments, thinking about the elastic fracture problems. But then you can also leave the interrogators out for many months to get long-term melt processes and see environmental change of the glacier through longer periods of time. And the equipment itself is becoming quite easy. One for transportation, thinking about large arrays that require a lot of equipment movements. This is fairly minimal in comparison, and it's becoming more and more cost effective as solutions are being developed just for geophysicists, and more companies are competing over instrument improvements and such. So with that, I'd like to stop and then be happy to take questions either now or at the end if we have time.
Thanks, Jam.
I have a question. How difficult would it be to deploy DAS down boreholes in temperate ice on the ice field?
Relatively simple. I think the drilling would be the hardest. Once you drill the borehole, it's easy to go in after and put the fiber down. I've done it in a water-filled borehole. All it really requires is a weight to make sure that you hit the bottom. And I've hand lowered the cable itself and pulled it back up over the course of over a 300 meter thickness, so it doesn't really weigh a lot either. So you don't really require uh, uh, a winch or anything to pull the cable back up after you're done. So quite simple, I think.
If the borehole's not water filled, do you have to keep it up against the side for coupling or?
Yeah, that's the tricky part. If it's yeah big enough in Greenland, if you think about Greenland, it'll freeze in over the course of maybe a week or so, or some time period it should be able to freeze in. I've deployed in boreholes in Antarctica where it stays somewhat uncoupled in some parts. If it's deep enough, then the cable will tend to lie on one wall or the other. So you can still have some sensitivity there. If the borehole is water filled, it might be a bit more tricky, and depending on how you suspend the cable in the borehole, you might lose some sensitivity. So that's certainly something to think about. I think anything deeper than 300 meters, you'll probably end up lying the cable on one wall or the other, or it'll be resting just because the borehole itself isn't going to be vertical.
Awesome. Thanks, Jan. Thanks, John Mark.